I will be presenting on acquisitional rule-based engine for discovering Internet of Things devices. The original paper is included in 27 USCNIX Security Symposium in Baltimore in August 2018. The details of the paper presentation and the authors are listed here. This presentation is about acquisition rule based engine, so we'll go through the background of the problem and how acquisitional rule based engine can have the solution for the problem, and the design and implementation of the acquisitional rule based engine, real world evaluation, ARE based applications. So I'll be referring acquisitional rule based engine as ARE in some of the places when I talk about. So ARE is acquisition rule based engine. So let's see the problem and how acquisition rule based engine has a proposal to solve the problem. So the Internet of Things are the devices that are connected to the internet. So these days more and more devices are getting connected to the internet because we want smart devices like cameras, TVs, smart devices that can like control the temperature at home or control the garage doors or control the devices in the kitchen, and some like voice controlled assistants, and in from home to industrial control systems and medical equipment. More and more devices are now connected in the internet for its operations. So Gartner reported that nearly 5.5 million new IoT devices were getting connected every day in 2016 and are moving towards more than 20 billion by 2020. As these IoT devices keep increasing, we need to think about the security challenges of the IoT devices. These devices can be vulnerable or mismanaged or misconfigured, and when they are increasing in such a fast pace and increasing in all domains, we need a way to commonly identify, like the discover all IoT devices and annotate them. So this is like a prerequisite to handle the security issues of the devices. So in this paper, they proposed an acquisitional rule-based engine. This engine can automatically generate rules for discovering and annotating IoT devices. The device annotation in this context is a combination of device type, device vendor, and product name. For instance, a device type could be a router or a camera, and a vendor could be Sony or Cisco, and with the product model like TV IP302P. So traditionally, or like in previous works, the device annotation was done either to fingerprinting based discovery or banner grabbing discovery. So fingerprinting discovery is so banner grabbing discovery is more like a manual using Nmap with technical knowledge, but it is more manual, so large scale annotations are hard to be done, and as the new IoT devices are coming up, the new ones are hard to get updated like manually, and in fingerprinting based discovery is based on like machine learning technology. So for machine learning to work, you need large amounts of training data, and large amounts of training data are not available for IoT devices. So this proposed solution in this paper, i- because it automatically generates rules, it is less manual in nature, and um, and the annotating is not based on trained data but based on a rules. So you don't need much training data for that. So to understand how it is implemented, first need to understand the key observations that they have done. So one of the key observation they have done is to, for when in, when we interact with IoT devices in the application layer protocol, the response data has some manufacturer information. So the response data is highly correlated to the context of their manufacturers. That's the one observation they did. The second observation is that internet has so much resources describing the devices. For example, product information. When a new product is released, they could put product pages, and then product review websites or Wikipedia. So this rule-based automatic rule engine is mainly based on the relationship between this application data and the corresponding description pages. So the transaction here is identified as a mapping between the response from an IoT device and to its product description in the website. The ARE utilizes this transaction data set to mine the rules. The ARE collects the transaction data set by first going to the application layer response data from IoT devices and using that response data. Once it gets the response, it clears up some information from the response. It cleans the data, and it also cleans up all the dictionary words, because most likely dictionary words are not the ones related to the product. I mean, product information like product vendor or product vendor or product model, they won't be in the dictionary. So it cleans up that information, and it identifies some keywords which it thinks are relevant. So using those keywords, it forms an URL with those keywords, a search URL that it can use to search the some search engine like Google. And so this ARE then goes through those web pages which are resulted out of the search, and it uses the web pages, and it does the name entity recognition to extract device annotation, including the device type, vendor, and product. It has also built in some intelligent logic along with the name entity recognition, like how do you exactly get to this device type, vendor, and product. But the idea is, after it generates the rules, then it puts into a library. So, and it also provides a RESTful APIs for other applications that wants to use those rules in those applications. We will see some of the applications using these ARE rules, how they are how they are using these rules. Coming to the design and implementation part of the ARE has 4 components: transaction collection component, rule miner, rule library, and a planner. This is a high level overview of the architecture. So the transaction collection component interacts with the network to get to transaction sets. And then these transaction sets are given to the rule miner. So the transaction sets um, contains the information from the web pages, information from application level data. So these transaction sets are given to the rule miner. The rule miner takes the transaction sets and then mines the data and generates the rules. These rules are stored in rule library. Different applications and wanting the rules can query the rule library through the API and get the rules. And then they can also use Planner to update the rules. Going a little deeper on how actually transaction collection component collects the transactions. So the transaction collection component is a component that gathers the data in the network and gives it to the rule miner. This works in two steps. First step is to collect the response data in the network and filter out the responses of the non-IoT devices. The second step uses the web crawler to obtain the description web pages of IoT device, then removes the redundant content from the web pages. And then it forms a transaction. So transaction can be thought of combination of two things. One is an application layer data and the second one is a description web page. So for example, if a response packet of an online IP camera has a term TLWR740 in HTML file, we use TLWR740 as a search query in the Google search engine or some other search engine to obtain a URL list including the description documents. Once you have these, like the keywords and then the description documents, this transaction is formed. So the transaction is more of a textual pair of textual units. So here the transaction data has more like a text format. So now this transaction is passed to the rule miner. Now the job of the rule miner is to take this transaction data and come up with the rules. So the rule is defined as an association between the features extracted from application layer, keywords, and then device annotation extracted from web pages. So this rule miner, they have defined the device types and vendors are predefined information. So they have identified 21 device types, 1552 vendor names. So for these device and vendor names, this rule miner finds out more of models and product information within those device type and vendor information. So the rule miner works for these device types and the vendor information but finds more products in it. As the device types and vendors are limited information, if a new device type or vendor is identified, they are added to it, but product information is automatically identified in the network. So here in the bottom diagram shows how rules look. So rules are the combination of, on the left hand side is the keywords and on the right hand side is device type, vendor, product information. So this rule miner takes the textual information, uses a logic built in it, and it has some intelligence built in it, like some conditions, like in most of the web pages, vendor entity comes first, followed by the device type and followed by the product entity, and it also takes care of some confidence level once it identifies the rules. So that's the logic of the rule miner. So it has some intelligence built in it which takes the transaction data and comes up with the rules. So once it has the rules are stored in rule library with a timestamp, and different applications can interact with the ARE through the API, and then rule library will return the latest rule for the users. Planner module is for updating the rules on the applications. If some application sees the rules are not enough, it can ask for the API to update, giving some network runtime. So the planner module will generate new rules in the current network and gather that data from this base, and outdated rules will be removed, and then those rules will be given to the application that is of the interest. So they have done some real world evaluation on 2 data sets. First data set randomly chooses 350 IoT devices from the internet. In this, they have identified 4 different device types: NVR, NVS, router and IP camera, 64 different vendors and 314 different products. In the second data set, which is of 6.9 million IoT devices that our application collected in the internet, so randomly sampling 50 IoT devices iteratively for 20 times, 1000 devices across 10 device types and 77 vendors have been identified. And the number of rules generated by ARE are far greater than the number of rules generated by Nmap. So this study generated 115,979 rules in 1 week compared to 6,514 from Nmap. 92.8% of the rules have all the device type, vendor and product information identified. Only 7.2 rules just has device type and vendor. The precision of rules in the first data set is 95.7 and in the second data set is 97.5%. The coverage of the rules is 94.9%. Given the same number of response packets, ARE achieves a larger coverage than Nmap. They also have used this ARE in 3 different applications. First one is internet-wise device measurement. ARE greatly facilitates such internet-wise measurements to detect IoT devices. So overall, we found 6.9 million IoT devices. The next application is compromised device detection. So this detection of compromised IoT devices is based on the capture of the malicious IoT traffic behaviors. So the honeypots are deployed in different locations all over the world to monitor for traffic on the internet. So normally no device should connect to these honeypots. So if they are connecting to the honeypot, it's most likely because they are not configured correctly or they are compromised. So when some device connects to this honeypot and that IP address is captured, and this compromised device detection process sends a request to the device, and using the response data and using the keywords in the response data, it identifies the IoT devices which are compromised. The other application is vulnerable device analysis. So it can help us find out which online devices are still vulnerable and perform security patches for critical infrastructures immediately. Vulnerable device analysis (VDA) first crawls the vulnerable information from the NVD website. For each vulnerable information, VDA obtains their vendor name and product name. Rules of those devices are extracted from ARE And these rules are used to discover new vulnerable devices with a high probability and then group those devices into a category of this vulnerability. So these three applications where use the ARE. So we have seen like the problem statement and how ARE um, is presented to solve the problem. So this ARE automatically generates rules for IoT device recognition. So it reduces the human effort in the sense that the rules are automatic. So it is adding to the device recognition so that you don't need to do much human effort, so it automatically detects the rules. And there is no training data because it is based on rules. So it is a solution that works for the scalability. So it automatically generates rules and identifies the IoT devices. And they've seen the effectiveness of the ARE because it is more fine grained than the existing tools. It discovered more rules, as we have seen, and in the study of the three applications also, it has provided the good results, and ARE seems to be useful solution for identifying IoT devices. Thanks for listening to my presentation, and if you have any questions, please ask on Piazza.